I don't know. So if you are out there and you you want to voice your opinion on whether or not, we were talking about now we're alive. We were talking about whether or not people like the hybrid approach to a course like this. Make sure that you talk about that in the end of term course evaluations. Again, it's my impression that people like the hybrid approach because they have a choice, they have a backup, they can go back to the lectures and look through them. The only drawback is that far too many people, don't go to lecture and then they intend maybe to watch the lecture later on, and then they don't. And then when they ask a question of, how do I do this? And well, I showed that to you in lecture. You might want to go back to that. Well, you have it, right? But that, it does require some sort of, personal responsibility, I guess. I don't know, discipline. But in any case, let me know about it in the course evaluations. Go ahead.
Last semester there were times towards the end where that was like my first class in the morning, and sometimes it'd be like, yeah, I'd rather just like stay and watch on a live stream or something.
It was like 10 o'clock, wasn't
Yeah,
it?
that was my first one. So there were times that I really didn't want to go out and watch it.
All right, fair enough.
Like this semester, my class right before this is like 2 doors down.
Oh, okay.
So there's no point in not.
Right. All right, well, we're going to continue with algorithms and algorithm analysis. And to do that, I forget whether or not we defined what an algorithm was, but we'll do that now, right? And so algorithms, right? An algorithm is an unambiguous sequence of instructions for solving a problem. Now, if you like that definition, great. That's the definition we're going to use. That's Webster's, right? That's not a mathematical definition. If you want a mathematical definition in order to talk in a more mathematical, rigorous way, then in Computer Science 3, you'll be exposed to Turing machines. And that's the mathematical definition of what a computer or what an algorithm is. There are alternatives like lambda calculus and a couple of others, and those are all mathematical definitions, and you can show that one mathematical definition is equivalent to another mathematical definition using the language of mathematics. Unfortunately, this is a dictionary definition, which is a completely different language, right? You can't reconcile dictionary definitions with mathematical definitions because one is rigorous and the other is not. And this is not a rigorous definition, but it's the definition we're going to end up using. It is what we can understand this a little bit more by saying what an algorithm is not. An algorithm is not a Java program. Right? A Java program is an implementation of an algorithm, right? An algorithm is not a snippet of code or a function. Function or a method, etc. Right? An algorithm is more generic, abstract concept than those things. Now we do like to make our code abstract and general because that's what polymorphism is all about. We can write one function or one class to hold any element that we want in a linked list implementation, right? But an algorithm is more general than that. It's just a process, okay? To describe an algorithm, we use what's called pseudo code. Because it is not a Java program, it's not a Python program, a Python script, etc. Right? It's not a C program, wwhatever. Instead, we use pseudo code, pseudo fake. Like I was fishing for another word that used pseudo in it, and thankfully, somebody in this morning's class said pseudonym, right? What is a pseudonym? It's a fake name, right? It's an alias. So pseudocode is just fake code. It's not going to be any particular language, right? Good pseudocode, if I could give you rules to follow for writing your pseudocode, guess what? You've got a computing language, right? You've got a programming language. That's what Java is. That's what Python is. It is a set of rules, syntax rules, for designing a program, to implement a program. Good pseudocode doesn't have those rules. They just have guidelines, right? It makes good use of English, plain English. Right? It makes good use of math notation, right? And I will try to stay light on it under the assumption that maybe we have, maybe we have not seen this stuff in 235 yet. But I'll probably use it more in this section, right? It doesn't use language-specific constructs. So we're going to stay away from whether or not something is stored in an array versus a list versus a dictionary or something like that. We're going to stay away from those language-specific constructs. We're not going to have semicolons. We're not going to use square we're not going to use curly brackets to denote code blocks, etc. Right? It gives essential details and omits unnecessary details. So what do I mean by that? Well, it's kind of a balance, right? As an example, suppose that I needed to describe a sorting algorithm, and I just had one line of text that said sort it, right? That's too terse, right? That's not enough detail. But if I were using a sorting algorithm as a subroutine to another algorithm, then it's perfectly fine to say sort the elements in increasing order, then go on to step 2, then go on to step 3, go on to step 4, right? That's sorting a subroutine that is not relevant to the algorithm that I am describing right now, right? So you give the essential details and you omit unnecessary details. The idea is that you can take good pseudocode and translate it to any programming language. Right? If it's good pseudocode, you should be able to do that. Right? And a lot of times, especially in Computer Science 1, that's what you do. Before starting writing code, you put in comments, step 1, step 2, step 3. You write some pseudocode out, then you go back and you fill it in with the actual code to implement that stuff. It's much better if we just do an example. So remember how linear search works. Right? Given a collection of elements, right, and a key, right, search output, or determine, I should say, well, determine. Does there, in fact, I'll use my math here. Does there exist an element A in A such that A is equal to the key element K? Right. Do we have that language in our, or do we have that symbol, those symbols in our language? Right. There exists quantified logic? No?
Oh, well, in 235.
Yeah, say 235?
Not in Java.
Oh, no, certainly not in Java. There are programming languages where you can do something like this, right? What does it mean for exists? It's just a for loop, right? Because you're doing it over a finite universe of discourse. What about this guy right here? It's like backwards epsilon. It's in, right? A in the collection, and then of course we've got these brackets and then equals here as our predicate. So this is a quantified predicate, first order quantified predicate. Right? That's what linear search is in mathematical terms. So let's go ahead and start writing good pseudocode to do this. Okay? Good pseudocode, again, it's a guideline here, right? But you should clearly label the input, clearly label the output. Okay? The input here is a collection. Is it an array? Is it a list? Is it a dictionary? Nope. Right? A collection, you give the collection a name. And then you use math to describe the collection, ... It is a finite collection. Not only that, but we tell you exactly how big the collection is implicitly. There are n elements in the collection, right? And we've indexed them. Mathematicians index things on 1. We as computer scientists index things on 0. Why? Because that's how memory works. Right? And a key, K. Here, I'll say it's a key. Good use of English, key K. Is this a collection of integers? Is it a collection of strings? Is it a collection of whatever, right? Who cares, right? We're keeping it general. My output is going to be an element, A in A, such that, here, ST, such that, that's a common abbreviation, A is equal to K. Now, did I say that it conforms to the dot equals method? That there are two integers, so you can use equals equals? Nope, I use the algebra equals here. Good use of mathematical notation. So all I'm going to do is say for each A in A, if A is equal to K, then output A. I did not use colons. That would be Python. I did not use parentheses and square brackets because that would be C-style syntax, right? Instead, I'm using this universal vertical line to denote that, and indentation to indicate that this is a code block, this is a code block within that code block. The reason I like doing this is just a personal preference. The reason I like doing this is that you cannot do this with any programming language. IDEs will support this. You can do this with LaTeX. In fact, I'll show you what it looks like here, that this is not, come on, don't die on me. You should be able, oh, no. You should be able to charge from the connection. Yeah, it died. Okay.
Computer died?
No, well, yeah, that computer died. My iPad died. Everything else is perfectly fine, right? All right, fine. What? Say what?
Even though it's plugged in?
Yeah, that it should be able to charge from the port, but it ain't. And there's only one USB-C. So instead, we are almost complete. I'm going to go ahead and jump to the finish line here. Here's what it looks like. You've probably seen this before. It's from my CS1 book, linear search. Right? So here I did index it. For each A sub I in the collection A, do the following. If A sub I is equal to E sub K is the key in this case, then output A sub I, and then it ends. And then I output, what do I do if there's no such element? Well, I put that in my output here. I output phi if there's no such element. If this were a programming language like, say, Java, what would you do? You could throw an exception. You could return null, right? You could return a negative index value to indicate that it doesn't exist, right? That's kind of nonsensical in some programming languages that have a convention that negatives wrap around to the end of the list, right? Python does that. PHP does that. A couple of other languages allow you to have negative indexing. Like -1 would be the last element, right? For convenience, right? If this were a Python, you could return, there is no null, there is a, do we know Python? All right, there's none. Capital N-O-N-E, all lowercase. And then there's also a none type, because none is not a type, it's a value, and so the none type, the null type is the none type, right? Anyway, I jumped all the way to the end here, and there's your good pseudocode, okay? Darn it. And nobody has USB-C charging stations because I've been using USB-C now for 3 or 4 years, but nobody else has caught up.
Oh, is it like the smaller ones?
Yeah, it's the smaller ones.
Are they like faster or something?
Well, they're more universal. There's no, oh, I screwed up, I can't get it in. Oh, no, that's not the way it was the first time, and then over and over again. But they are, I mean, that's the standard now. It should be, at least. But even this laptop, this laptop has USB-C. Okay. My phone is like 5 years old, and it charges from USB-C. So why we don't have USB-C universal in classrooms yet, I have no idea.
Input and output are the exact same.
It's universally universal. But yeah, that's why I've got like a whole bag of adapters over here. Anyway, so that's the idea of pseudocode. Okay, it gives you the essential details without giving you any specific language constructs, and we'll do a couple more examples as we go along here. Okay. I can do good notes on here. It's just that I won't be able to use my pencil. We'll see how it goes here. Was this 156? Nope, sorry. Darn it, I don't see that 156 is on here, so I'll just go with this. All right. If I need to, nope. If I need to, I will go ahead and, there we go. This is just a doodle page that I've got up here. If I need to write, I'll try to write on here with my pencil. All right. There we go. Okay, good notes is still working. Just in case, but I don't know if we'll be able to. All right. Anyway, there's going to be a 5-step process once we have that that pseudocode, that we can walk through the pseudocode and follow this. Sorry, that's not what I wanted. Apologies. We're going to walk through this and do this 5-step process. This 5-step process is to identify the and come on, everything is off today because I had too much pizza apparently. Does anybody else go to pizza? No? Okay. Anyway, algorithm analysis. The first step is to identify the input. Then you identify the input size, n. You identify the elementary operation. You analyze the element, how many times the elementary operation is executed with respect to the input, and then you characterize that that equation or that formula using big O analysis. Right? The great thing about this 5-step process is that if you write good pseudocode, then the first 2 steps are completely done for you. Right? Here's our good pseudocode. What is the input? It's a collection of elements and a key, k. Right? Now, there are actually 2 parts to that input there. The collection and then the key. So there is a little bit of nuance even with this simple first step, right? Identifying the input. Again, it's generally given as part of the pseudocode, but if you've got multiple inputs, right, in some cases, you may have multiple pieces of input. What do you do, right? So, for example, in linear search, you have a collection and a key. Right? With Euclid's Gcd algorithm, we all know what a greatest common divisor is, right? It's the largest integer, A and B. It's the largest integer that divides A and divides B. Right? The GCD always exists. It's always at least 1, right? Because 1 divides anything, right? If 2 things are co-prime, right? If you got prime numbers 7 and 11, what's the GCD? It's 1, right? If you've got 77 and 7, the GCD is, in that case, 7, right? Euclid came up with the general GCD algorithm that's still the fastest to this day. Euclid's GCD algorithm has 2 inputs, right? 2 integers, A and B. Right? So what do you do in each one of these cases? Well, what do you do in, say, linear search? Which one of those 2 pieces of input is probably more relevant to the algorithm and the algorithm's behavior? The one that contains n elements and can be larger and larger and larger, or the key, which is only ever one thing? The key, right? Oh, well, sorry, the key, is the key the more relevant one? Sorry. So will this algorithm behave better with, will this algorithm behave the same with, say, 1 million elements versus 10 billion elements? Probably exactly the same. You have to go through all the entire. Now, granted, you could get into what's the best case, what's the worst case, what's the average case. But generally, it's going to be the collection here, right? Because the key is only ever one thing. But n could be 10, it could be 10 million, it could be 10 billion, right? And as it grows, that's what the algorithm is going to be affected by. It's not going to be affected by the key, okay? So in general, sorry, go back here. You keep it simple. Select one of the inputs as your input, usually the most relevant one. Okay? So for linear search, that would be, here, I'll just go in like this. Linear search, that will be the collection. What about Euclid? Euclid's GCD. Do we choose A or B? Either. Okay. I'm going to go ahead and put a small writer on that and assume that A is greater than B. Right? Then choose A. Actually, I'll even say it's greater than or equal to, right? Because it could be that A is equal to B. In which case, the GCD of A and B when A is equal to B is A and B, they're equal, right? Then I'm just going to choose the larger one, right? I.e. the larger one, i.e. the larger one. Okay. Why? Why is that relevant? Or why is that an okay assumption, right? To simplify it. Well, think about it like this. Suppose that you wanted to do both, right? Suppose you consider both A and B. Then the input size is no greater than 2A, or 2A, right? Why? Because that's less than or equal to, greater than or equal to A plus B. Why? Because I said that A is greater than or equal to B, right? And in the end of the day, what's going to happen to that 2? Yeah, well,
A is greater than equal to B.
A is greater than equal to B. Oh, well, yeah, that 2, when we analyze it with respect to big O analysis, we end up throwing out those coefficients because we don't care about coefficients, because we can always take it from one piece of hardware to another piece of hardware that's twice as fast, and those coefficients are now cut in half. Right? My math is right, right?
What I was trying to say was that, like, you could subtract A on both sides, and then it just becomes A is greater than equal to B, right?
Yeah, well, then you, oh.
That's the same thing.
That's the same thing.
Yeah.
Yeah, that's what I was trying to say.
Okay, sure, yes. Math. My undergrad was in math, so. Anyway. Keep it simple is the takeaway here is keep it simple. If you've got an algorithm that has multiple inputs, choose one of them and stick with it. Be judicious about it and just use some common sense, okay? The second part is also a little bit nuanced. You identify the input size, right? Usually you use the variable n to denote the size of the input, right? Generally it's easy. For example, if it's a collection, then it's the size of the collection, right? If it's an array and there are n things in the array, then n is your input size. What if it's a two-dimensional kind of thing? What about a matrix or an image, right? Say an n by m matrix or an n by m image, right? Well, once again here, you can simplify. Assume that n is greater than or equal to m. And then what can you do? Then m plus n is less than or equal to 2n, right? Or another way of saying this is what? So that n times m is less than or equal to n squared. That's what you said, right? Yeah. So in other words, again, simplify, right? If you've got a rectangular image padded out with a bunch of pixels that don't matter, and now you've got a square image that's n by n, just go ahead and keep it as n, right? If you've got a matrix that's n by m and it's not perfectly square, pad it out with zeros, and you've got an n by n matrix, right? Just simplify it, just take it down to one variable. Because if you do keep two variables, guess what? The function that you end up coming up with is going to be a two-variate function. And you're not going to have this nice, quadratic in the Euclidean graph. You're going to have this surface in 3 space, and that's hard to reason about. Right? But sometimes it's not generally easy. What if the input is a single number, say an integer, right? X. For example, Euclid's GCD algorithm. We already said let's simplify it and we'll only consider A or B. Right? And now I'm naming it X. What is the input size of a number? Right? If you're a computerist, right? And or like an actual engineering, everything's a 32-bit number, right? It's a constant number of bits, like 32 or 64, right? But then we all know that if you only use 32 bits, the maximum number that you can represent is 2.147 billion, right? Well, that's a computer thing, right? And remember, pseudocode. We're staying away from computer things, right? All right. So suppose that you have a very large number, right? Would you agree that there's a difference between 1,234 and here, I'll just go ahead and mash out the keyboard there. Is there a difference in the size of those numbers? Yes. So how can we quantify that? What do you mean linear? Well, okay, certainly it's going to be higher over here because, right, if you map it on a linear function, then the value is way over here, up here, and the value is way down here, sure. Well, we already have a way of doing it in a computer. The number of bits it takes to represent it. When we're not talking about a computer and we're talking about a piece of paper or base 10, what are we talking about? The number of digits, right? So the input size of a number is the number of digits or bits or other symbols needed to represent it. Okay? So for all of us normies that go base 10, how many digits does it take to represent x? The number of digits to represent x is? Oh, there you go. Divide by 10 once, that'll 5-digit number, that'll get you down to a 4-digit number. Divide by 10 again, divide by 10 again, divide by 10 again, divide by 10 again. The number of digits is the number of times you had to divide by 10, which is equal to log, right? Is log base 10 of x, right? All right? The number of, and this is a word, digits, right? But that's what it was originally called, right? But we shortened it because that sounds weird. We shortened it to bits, right? The number of bits to represent a x is ... what? Log base 2 of x. Exactly. Decimal, right? Deca, right? Dodecahedron, right? A decimal, decameters, right? 2 though, bits. Binary? Yeah, binary, but what's the... Binoculars. Yes, all that stuff. Okay, so this is when you put on your mathematician's hat, and remember, why is e the natural base? It's because the first derivative of e to the x is e to the x. Does it make sense to talk about a numerical system where there are 2.71 symbols that you can use? No, that's an incomprehensible system. Is there a system where you can use one symbol? It's called unary, right? And so you want to mark out the number of days you've been in prison. 1, 2, 3, 4, and then a slash through it for 5. Roman numerals are kind of like that, right? 1, 2, 3, and then it gets a little bit janky with IV and V and stuff like that. But you can do that, but none of those are efficient at all. Binary is efficient. Decimal 10 is efficient for humans. And in fact, other human-based mathematical systems have used even more. I think that there's one that was, the Babylonian system was base 60, no, that doesn't sound right. Base, I want to say, what was it? Base, they used like 14 or 15, or no. They had many, many more symbols because of mathematical tricks that they could do with their algebra. We like base 10 because we've got 10 fingers and 10 toes. That's how we count, right? So why don't we have base 10 computers? Does anybody know? You could, but what would you have to do? You'd have to have 10 different states instead of just on or off, or high voltage or low voltage, or vacuum tube vacuumed or pressure or not pressure, right? Then you'd have to distinguish between all 10 of these, right? Between very high voltage, slightly high voltage, slightly less high voltage, slightly, right? There's too many, and it's way too error prone. But base 2, far less error prone, right? You can distinguish between 0 and 1 much easier than you can distinguish between 0 through 9. Right? And that's why there have been computers that have been base 10, and they've been problematic because of those errors, right?
Isn't that what they're trying to do with like quantum computers? Because they-
Quantum computers still use qubits, which are zeros and ones, but they are in a superposition. So you can set up a qubit to be in a probability between 0 and 1, right? And then you can not anneal them, but you can massage them in a quantum circuit so that when you finally say, all right, measure it and collapse the state has a high probability of being in a correct answer or not a correct answer, and low probability of being in a bad answer, right? Depending on what you're trying to do, right? So it uses quantum mechanics and measurability and superposition to exploit that kind of computation.
It's still binary.
It's still binary. Yep. Okay. So the number of bits required, right? And that's going to be log base. And then you can go ahead and take a ceiling, take a floor, because log base 2 of a number could be an irrational. In fact, it will likely be an irrational number. And so you just round up to the nearest integer to say that this number will require 50 bits to represent. Right? Do we know why that is? And unfortunately here, I'm going to have to, can I type? No, okay, I'll do it right here. I can type it a lot easier. All right, so suppose I gave you k digits to represent a number, ... with k equals 1 digit, the max number you could represent is ... 9. Okay? Repeat. With k equals 2 digits, the max number that you could represent is 99. With 3 digits, it's going to be 999, and you start to see the pattern. If I just gave you k digits where k was not specified, then what could you represent? 10 to the k. Well, it did okay right automatically. I don't know why it did that. But minus 1, that's an undocumented feature right there. Right? 10 to the k minus 1. Now, repeat that for bits. Right? If I gave you k bits to represent a number, to represent a with bits, the max number you could represent is 2. Oh, well, sorry. If 1 bit would be 0 or 1, so it'd be 1, right? With 2 bits, the max number that you could represent is 1 1, which that's binary now. 1 1 is going to be 3. Right? With 3 bits, it's going to be 1 1 1, which is 7. Right? And so in general, and this is why it's binary, instead of 10 to the k, it's going to be 2 to the k. Right? 4 minus 1 is 3. 8 minus 1 is 7. 16 minus 1 is 15, etc. Right? And so now reverse the question. Right? Given x, right, which is, say, a maximum value of 2 to the k minus 1, the number of bits, that is k, to represent it is ... How do I solve for k there? Well, I can take plus 1 to the other side. X plus 1 is equal to, and then I've got 2 to the k on this side, right? And now take log base 2 on each side, and what do I get? Log of 2 of x plus 1. Now, who cares about plus 1, right? You're going to take the ceiling anyway, so just go ahead and increase it. Log of something. Log of x is good enough, right? There's no way to break that up, unfortunately, symbolically, right? If it were log of a times b, then you could break it up into 2 logs, but you can't do that here. Right? So this is why it works, right? That's the whole purpose of a logarithm too. Right? That's one interpretation of a logarithm, that it tells you how many bits or how many digits or how many e's it takes to represent a number. Right? The math works out, it's just that you can't express it, right? That's with a lot of things. The math still works out with a lot of things, it's just that you can't visualize it. You can define an n-dimensional state where n is 10, like a 10-dimensional state, but you can't visualize it because we're 3-dimensional beings, right? Okay, so that's identifying the input size. Third is the elementary operation. And this is where you've got a choice, right? Ultimately, you want to characterize the algorithm's complexity, or the amount of work it does. So what do we mean by work, right? We only want to focus on one operation, right? So let's go back over here to the linear search algorithm right here. We're doing a lot of stuff, and we're doing a lot of stuff implicitly here, right? If this were a regular old Java program, what would I be doing? For int I is equal to 0, right? I'm creating a variable and I'm assigning it a value. 2 operations right there. While I is less than n, I'm doing a comparison. I++, I'm doing an increment, I'm doing an addition, right? So already, and then I'm doing another assignment to reassign the value of I. So I'm doing assignments, I'm doing comparisons, I'm doing additions, right? And that's all just in line 1, right? Then I'm doing another comparison right here to see, well, I'm also doing a memory jump to the ith value, loading the ith value up into memory, loading the key value up into memory in some register, making a jump to a comparison, compare the 2 values in these registers, and if they're equal, jump to this memory location, otherwise jump to that memory location. Right? So when you think about it at the level of a computer, at the level of the hardware, I'm doing dozens and dozens of different operations. Right? I don't like to think about that. Right? Nobody wants to think about that. Keep it simple. Right? Don't think about operations that are necessary for the control structure of your algorithm. Right? Whatever you're doing inside this loop is going to be proportional to whatever you're doing to execute this loop. So don't pay attention to anything that's going on in the loop, right? Or for the purposes of the loop. Think about what you're doing inside the loop. Right? That leaves this line and this line. Are we always going to be executing that innermost line? Nope. But we all are going to be executing this line. And what are we doing here? A comparison. Right? So keep it simple. You only want one operation. Again, for linear search, it'll probably be a comparison. Right? So for some, math operations, addition, subtraction, subtraction, or multiplication, division. Right? Why did I put slash between those? Addition and subtraction. Why are they the same thing?
Because subtraction is just adding a negative number.
Exactly. A subtraction is nothing more than addition of a negation. Right? And why is multiplication and division together? Your division is nothing more than a multiplication of a reciprocal. Those are the things. But between those 2 groups of operations, which one is more expensive, do you think? Is that more complicated? Yeah, probably multiplication. Why? It's iterated addition. 5 times 10 is nothing more than 10 added 5 times. Right? So you could always implement multiplication using addition. So multiplication, you don't do it that way. You design a circuit to do it, but then you're only doing it for 32-bit numbers or 64-bit numbers or whatever, right? We want to keep it more general, right? What about our experience with linked lists? What were we counting up in our demonstration way up here to say that something would take 20 plus years? A node traversal, right? So if you're going from one node to the next node to the next node to the next node, that's your elementary operation, right? This also applies for graphs and trees eventually. What if you have the choice among several different ones? For example, sorting. right? You're going to be doing comparisons. You also might end up doing swaps, right? Well, there you have a choice. There's not one choice that is better than another. Right? It's just how are you, if you analyze it with respect to comparisons versus analyzing it with respect to swaps, you will get different answers. Both of those answers are correct. Right? It's just your perspective. Okay. Finally, the analysis. Right? You simply come up with a summation or formula to characterize how many times the elementary operation is executed with respect to the input size n. Right? Respect. There we go. Right? This gives you a function, right? It gives you a function mapping the natural numbers to, right arrow, the positive reals, or at least the non-negative reals. Right? And again, why do we consider the natural numbers here? Because we don't have negatively sized inputs. We don't have fractional input values. And why do we focus only on positive reals here? Because there's no such thing as an algorithm that takes negative time, right? You have the answer in the past, right? Like it's a time machine of some sort. Okay. Again, this might involve a summation and solving summations, etc. We might end up doing some math like this. You can always go to your old friend Wolfram Alpha and throw it in and have it solve it for you, right? Doesn't really matter. Right? This is not a summations course, right? But generally, we will be interested in an upper bound on the complexity of an algorithm. For example, linear search here. You could get lucky. Right? How would you get lucky? If you find it the first spot you look for it, right? In which case you would end up making one comparison. You might get unlucky and find it in the last position that you're looking for it. Or you might not find it at all and end up having to output phi here. Right? In which case you made how many comparisons? N comparisons. Somewhere in between that. Best case scenario, worst case scenario would be the average case scenario. The hand-wavy way of doing that is just by taking n plus 1 and dividing by 2, so it's n divided by 2. Right? N divided by 2 is still linear, and that's why it's called linear search. Right? Even on average, it's going to be linear. Okay? But we are interested mostly with upper bounds. We don't want to get all optimistic and assume that we're going to have the best case every single time. We want to know what is an absolute worst case scenario on the amount of memory or the amount of time required to execute this algorithm with respect to the input size. Okay? All right. The fifth step is, of course, asymptotics. Asymptotics. And you've seen it probably before, big O analysis. Order n, right? Order n squared. O. That's actually not an O. Do you know your Greek? Omega would look like this, and that is an asymptotic, but omega looks like that. A horseshoe. So O is Omicron. Is it? Is it Omicron? The newest variant is some weird number, isn't it? Like VA2 or something. I don't know. But the Omicron variant was the last one to go around before this one. Yeah, they just increment. So Omicron was the oath one. It was like the 13th or 14th variation that they had actually phenotyped or whatever. They just went in sequence, I think. Anyway, I'm not a virologist, so I don't know. But I do know that that's Omicron, which is so close to our letter O that in fact there is no LaTeX for it. I'm not writing Omicron. In fact, Omicron is not even supported in LaTeX. There's a little omicron, but guess what it looks like? It's not, it's little o, right? What is big, maybe there is a big omicron. Omicron. Nope, there is no big omicron, but there is a little omicron. Right? But it is no different than our English, or English letter O? It's not really English. What is our alphabet from? It's an adaptation, I guess, from Greek? Okay, whatever. Latin, whatever. Anyway, we just use this as a placeholder. It allows us to ignore lower order terms. It allows us to ignore coefficients, constants, right? And just get down to the nitty-gritty growth rate of a function. That's where we'll have to pick it up next week when I've got a fully charged iPad. But otherwise, we can go through the first 4 steps with linear search today. Right? So let's do this as an example. Linear search. I'll go back and forth here. Step 1 is done for us. What is the input? The collection A. 2. What is the input size? N. The number of elements in it, right? The input size is N, the number of elements in A. Right? Like I said, good pseudocode gives you the first 2 automatically. Right? 3. What is our elementary operation? Comparison on line, what was it? 2. So another good tip when writing pseudocode is, just like regular code, number your lines so that you can refer to them. Right? 4. How many times how many comparisons do we do for a collection of size n? Right? In the worst case, n. Right? And we already said in the best case, 1. Right? Average case, it's going to be 1/2 n. I'll write it like this. Right? There we go. N over 2. You like that better? Which one? Or less compact and divided by 2? Okay. That way, fine. All right. So, which one do we pay attention to? Probably the worst case here. Right? Because ultimately, we're going to ignore that 1/2 sitting out front when we go to step 5, asymptotic analysis. And jumping ahead on that, it's going to be order n. Right? In other words, it's linear. Who would have thunk that an algorithm called linear search would have a linear complexity? Right? Maybe in our last few minutes here, let's do another example from the beginning. Binary search. And for this, let's go ahead and, since I don't have my iPad, I won't write it by hand. Let's go ahead and go into text mode here. Right? Do we remember how binary search works? You split it in half. But what's required to split it in half, first of all? Nope, that's not what I want. Where's binary search? I'll have to go to computer science 1. Binary search, sort. Okay, fine. Here is an example. It's sorted. Right? Suppose that I'm searching for 102. If it's sorted, what do? I jump right into the middle. Right? And that's not the thing I'm looking for. So 102, where do I go next? Do I even bother looking at this half of the list? Nope. I go and look at this half of the list. And now in this half of the list, there are only 5 elements. What's my new middle? Right there. 102, the thing that I'm searching for. And so we're done. Right? Only 2 comparisons instead of 11 comparisons. Or if I started from 0, I would end up having to do 9 comparisons to get to 102. Right? So let's write some pseudocode for it. Do we want to do this recursively, or do we want to do this iteratively? Iteratively? Okay. So my input will be a collection A. Can I do code? Oh, I can't do code mode inside of. I can't do LaTeX inside of code mode. So A equals A 0 through n. No, 1 through n. There we go. We all understand that notation? Okay. I'm telling you that there are n elements in there and that we're going to index them on 1. And a key, k. Okay? And my output will be an element, a in A, such that A is equal to k. In other words, it's the exact same thing as linear search, right? Because it's the same problem. It's just a different algorithm for it. Right? So help me out. Where's my middle? N over 2? Okay, that'll work for the first iteration, right? Relying on integer truncation to take care of fractional values, because 5 divided by 2, 2.5 is not an index that's valid, right? Okay, there's the middle, right? But what else do I need to keep track of? When I, oops, where is it? All right, sorted array. When I jumped to the right part of this list right here, I needed to keep track of the endpoints, 6 and 10. So let's call that left and right. Okay. Where should I start my left and where should I start my right? Oh, at the very beginning, all the way at the beginning of the array, all the way to the end of the array. So that should be 1 and n, because we're indexing on 1 in the pseudocode here. Okay. That gives me pause about this first m is equal to n divided by 2. How do I keep that general? Right and left now, in terms of those two things. How do I get the thing right in the middle of two numbers? I could go left minus right, and that would give me this range. And then I could divide it by 2, and that would give me this range. But that wouldn't give me these numbers. I could just take their average. Right? Left plus right. If you have two numbers on the number line, how do you get the thing right in the middle? It's just their average. Now, this is pseudocode. Never ever do that in actual real code because of overflow and underflow. Right? That is susceptible to overflow right there. Right? Yeah. Underflow is just when you're going the other way, right? So if I go negative 2.147 billion and change and subtract 1, I'm back to positive 2.147 billion. Right? Okay? But I'm going to do that in a loop. I'm going to do it in a while loop. While these two indices are valid, left and right, when they're going to move in on each other, right? And zero in on that one element. When are they no longer valid? They get closer and closer and closer when they've gone past each other. So while the left is less than or equal to the right, then we continue this dance inward. Okay? I will recompute the middle each and every single time, and I will check if a sub m is equal to the key that I'm looking for, then output a sub m. Right? I am using colons here. This is too Python-y for me, but it ain't Python. You know what? This would be valid in Python so far. Except for, I don't know if it would like that or not. I don't think it would care, actually. Here, I can highlight Python highlight it. There we go. And it's highlighting okay. All I did was change this from text to Python, and now it's going to highlight everything. Right? Now output is not a valid Python. I know that for sure. This is not Python. Right? Yeah, you print or a return or something like that. Screw it. Let's write Python then. All right, that's an if. How do I do an else if? Elif. Right? a sub m, the key that I'm looking for is less than a sub m, then what do I do? Oh, here, comment. Search the left half, dot, dot, dot. So if I want to search the left half, then, and I've got left and right here, and I need to search this left half here, then I update the right to be m minus 1 because I've already checked for it. Right? So right is equal to m minus 1. Right? Else, if a sub m is less than k, then I will search the right half, dot, dot, dot. And I will update left to be m plus 1. Now, actually, I'm glad I wrote this in Python because do I need this final check here? Nope. It's either greater than, equal to, or less than. But I'm emphasizing the fact that this is the third value here. This would not be valid Python because then you need an, do you need an else? I'm not sure. But in any case, I will put else. And then I'll put as a comment that a sub m is less than k, so therefore search the right half, and the left gets updated. Right? And that's the end of the while. Right? What do we do after we're done with that while loop? If there's no such element, then what do we do? If no such element meant output. All right, let's be Python-y. None. And there. Okay. So in the end, I will output none. And you know what? This is so much Python, or this is so like Python. Let's go ahead and open up. Now, I'm trying to think of what do I have access to? I have access to Visual Studio. By the way, you might remember from Computer Science 1, we use the CS50 IDE. They are shutting that down, and they are instead giving everybody free GitHub associated Visual Studio online workspaces, and that's what this is. I've been using this up in Omaha. I'm going to go ahead and get rid of this stuff here. CD CS1 lecture. Now let's touch binary.py. Alright, and refresh this. Where is it? Refresh. There it goes. That was too quick. Alright. So let's learn some Python today. Alright. So you need to define this binary search. So def binary search. Right? Def is short for define. And we will take as input here an array, right? And a key, k, or k, right? Colon, that defines a function. One of the PEPs for Python is how to document functions. And it's kind of weird because you do it inside the function before the actual function right here. And you should be doing it with multi-line comment strings like this. That's 3 double quotes. And then to end it is 3 double quotes. Right? And so here you put your documentation in here. Okay. Otherwise, everything becomes, there are no square brackets. To denote code blocks, you need to make sure that your indentation is 100% correct. There's this great video where this guy was, ragging on Python, but being sarcastic about it. He goes, "It's great. You don't have you don't have curly brackets anymore. Instead, you only have white space errors." And then he cuts to a scene of him holding up a ruler to find where is that white space error. It was great. I should post it for everybody. But Python is 0 index, so we'll start our left at 0, our right at n-1. Note here that I am not declaring these things, right? Because it's dynamically typed. Right? There's left, there's right. You do have a while loop. Even though you do, it doesn't like you. It's not Pythonic to write parentheses when you don't need them. So it's okay with them, but it discourages you from using them. Right? And, oops, everything has to be indented correctly. And woe to you if you are using tabs versus spaces. Thankfully, my IDE, my editor here is forgiving enough that it's putting in spaces anytime I hit a tab. Right? We don't output things, we return them, a sub m. Right? In this case, I'll actually return the index at which I found it. Right? Right. Return m, else if, elif. It's less, then we search the right hand, and the comments, single line comments are hashes. There's right, else, and then I did make a mistake here. What do I need? A colon, right? So, wow, Python is so great. I don't have to do semicolons, except when you have to do colons, right? Big. The Python enthusiasts and Python, evangelists will always come up with these weird, positives of a language, and then you can just switch that around. Well, you have to use colons. No, oh, well, yeah, but that's different somehow. Otherwise, there's left, and I need to make sure that that's all aligned. This is not aligned. It doesn't matter inside of a block, but we should be consistent. All right. R sub, say again. Thank you. Array, or I could just change this to A. There we go. All right. Outside my while statement, I'm done, so I return. There is no null, there is none, and it's not none, it is none. There is true, there is false, but there is no true, there is no false. Okay, let's create an array so that we can test this. So lists, there are no arrays, there are lists, right? And lists are done with square brackets. So let me go ahead and make sure that this is actually sorted. I don't like making up numbers, so I'm going to steal those. -3, 2, 4, 4, 9, 12, 34, 42, 102, 157, and 180. There we go. No semicolon. Key will be what we're searching for before, 102. All right, and we'll go ahead and go with index is equal to binary search of my array and my key, right? And then print index, or found at index. What is concatenation? It is a plus. So what is addition? Plus. All right. What is concatenation of a string and an integer like I've got here? It's error. Python, first of all, let's make sure that we're on Python 3 because nobody uses Python 2. Python version. What?
Well, because you spelled Python wrong the first time.
Oh, is it? Okay. Unknown option E. Okay. Python version. Say what? Well, it's going to go and put me in REPL mode now. I'm actually. Oh, there. Thank you. 310. Thank you. All right. Quit or Control D. There we go. So we are on 3. Good. Python. Otherwise, if you were not on 3, you'd have to go explicitly 3. Binary. So we should expect that this is at index. What was it? 8. And it's error. Oh, there's a syntax error. Array sub m. Cannot assign subscript here. Why not? Equals. There we go. That's why. Being not Python-y enough. There we go. N is not defined. Yeah, okay. N is not defined. What is the size of an array? The length of an array. Yeah. Gross. Strings have length. Arrays don't have length. They have sizes. List indices must be integers or slices, not floats. All right, good Python lesson here today. Is there integer truncation in Python? Nope. 5 divided by 2 is 2.5 because there are no doubles, floats, ints, right? So, math thought floor. And if you're going to bring in math stuff, import math. This is turning out to be way more than I wanted to do. Okay, so K, it's key. There we go. Oops. There, that's the error that I was referring to. Finally, after all the other errors, you cannot concatenate like you can in Java. What you have to do, wrap it up in a string str, force it to explicitly become a string, and now it's perfectly happy. Right. So yeah, again, the Python evangelists you can come up with a million counter examples to anything that they say. Well, Python's such a much simpler language, right? You don't have to write int main. Like, you save one line, and I can find 50 other things that are just as annoying in your language as are annoying in every other language, right? Yay, we found it at index 8. What else should we be testing for here? Okay, things that don't exist. I want to test one of the extremal values here first to make sure it works. Index 0, excellent. What about the last one? That should be at index 10. Is that right? Yep. And then something that doesn't exist, like you said, something in the middle that doesn't exist, say 35. Right. This should output none. Yep, it does. So it turns out if it's none, you don't have to wrap it up in a string concatenation. Right. I'll show you. I'm pretty sure that this will still work. Nope, I guess not. You can't concatenate none type. Okay, fine. There we go. None before. And then let's make sure that it works on a really extremal example all the way up there. Doesn't find it. Guess what? Are they 32-bit integers? Nope. They are arbitrarily large if you wanted to. That's the one thing I do like about Python. Well, this is not true until Python, I think 2.7 or something like that, but they had native support for arbitrarily large integers. That's the one thing I do like about it. Yeah.
Why isn't it? Don't they always use like Python for like deep learning and machine learning?
That's just because people have written popular libraries for that kind of stuff. TensorFlow and OpenCV and stuff. Guess what OpenCV is written in? Mm-hmm. See, exactly. Under the hood, everything I believe, I could be wrong about this. It's still written under the hood in C. With Python, if I called math.square-root or math.floor, do you think that they actually implemented it? No, it's just calling the C library stuff. Right?
Wow. So it's really just C.
What do you think the Python interpreter is written in? C. Right? In fact, the Python interpreter is called Cython, or I think C Python. Right? But there's your first taste of Python. Your now fourth programming language, if you want to. Right?
Technically, can you write machine learning in C?
Oh yeah, it's just a pain in the butt. I mean, the more libraries that you bring in, the richer the language is going to be. I mean, some of the nice things about Python is like a set, for example. Foo is equal to a set of like 2, 4, 1, 5, 2. Print foo. I don't think that second 2 will be there. What? At most one argument got 5. Okay, fine. A set of. How do I think no. This is the syntax. Sorry. Like this. Right. There we go. Yeah, that second 2 is not in there. All right, it's a set. And then you can have a dictionary.
Did they order it?
Maybe, maybe not. Yeah, well, set is unordered, but they might be, imposing an order just for printing. I'm not sure. Don't quote me on that. But then you can have a dictionary, which you could have foo maps to. What is it? I think it's like this. 42 var maps to 101 baz maps to, very much like PHP, right? And a PHP associative array, and print var. Yep, there we go. So dictionaries, sets, lists are all built in. They're first class citizens in Python. You can use data structures in any language, right? Exactly. There's nothing special about Python. Frankly, I don't know why it's so popular. I don't understand it. But then I don't understand why social media is so popular, or why crappy movies are popular. But it appeals to people for some reason.
I took, I think it was like CSE 101.
Okay.
School online, and that was on Python.
Yep, Python. Were they Python enthusiasts? Like, Python is the best language ever.
I don't remember if he was particularly like thought it was great or thought it was bad. It was,
Okay, that sounds like a good attitude to take.
yeah, it was Reginald Bowman.
Okay. Yeah. Nope. All right. So there's Python. All right. Let's see. Oh, my OBS is on a different. We'll pick it up there when I've got an actual full iPad now. All right, there we go. And